I'm sharing my screen. Okay. Today we'll start about the test bench for combinational circuit. How to write the test bench for combinational circuits. Okay. So here, if you see the test bench. Test bench for how to write the test bench for combinational circuits. Okay. So here, if you see the combinational circuit, what are the combinational circuits are there? First, you have we already discussed first half adder, okay, and next you have full adder and half subtractor, full subtractor, okay, half subtractor, full subtractor, and ripple carry adder, okay, and carry look adder, BCD adder, VCD adder, okay, and next you have parallel subtractor, okay, next adder subtractor, okay, adder subtractor, mm, and advanced adders also there, advanced adders, okay, advanced adders, okay, advanced adders, and in the multiplexers, in the mux, you have first is 2 cross 1 and 4 cross 1, okay, 4 cross 1 mux, and in demux you have 1 cross 2 demux and 1 cross 4 demux, okay, and next one second, one second, please wait. Okay, go on. చెప్పు
క్లాస్ అవుతుందా?
అవుతుంది చెప్పు.
హర్ష వచ్చిందా?
వచ్చిండు, అన్నం పెట్టిన తింటుండు.
తింటుందా? ఒకసారి హర్షకు ఫోన్ ఇవ్వవా?
హర్ష, మమ్మీ కాల్ చేసింది చూడు, మమ్మీ కాల్ చేసింది చూడు. యా, see here. So here, if you see, yeah, unmuted my mic. Okay, yeah, see here. Uh, so next you have so demux and decoders also. Okay, decoders. What are the decoders? You have decoders 2:4 decoder, 2:4 decoder, and next you have 3:8 decoder. Okay, encoders, okay, encoders, you have 4:2 encoder, and you have 8:3 encoder, 8:3 encoder, and code converters also, code converters, okay. What are the code converters? You have BCD to decimal, BCD to decimal, and next you have binary to gray, binary to gray, and gray to binary, gray to binary, and comparators also there. Comparators. What are the comparators? You have 1-bit comparator and 2-bit comparator. 2-bit comparator. For all those things, you need to write the you need to write design as well as test bench. Okay. One second. I will open one PPT. It's not okay. One second. Yeah. I'll open one PPT. So test bench. Okay, what is this test bench? We are going to generate the stimulus and provide it to the design and check for the input. Okay, so test bench is nothing but what is test bench? Okay, test bench is I'm changing the color. Test bench. So we are discussing about test bench. Test bench. Test bench. Test bench is nothing but so we are going to generate. We are going to generate. We are going to generate the stimulus. Okay, we are going to generate the stimulus. Okay, and provide it to the provide it to the design. Yeah, provide it to the design. Yeah. Okay, so this is my design. Okay, this is basically my design. Okay, so for this design what I am giving. So for this design, one second. mm, yeah, yeah, for this design what I am giving. So this is my test bench. This is my test bench. Okay. So these are the for the design I'm giving the inputs, I'm getting the outputs. Okay, for this design I'm writing the test bench. By the test bench I'm giving the stimulus. Okay, so based on that stimulus I'm getting the output. Okay, that is nothing but test bench. Okay, so so basically like so first we'll see the program for half adder. Okay, so program I will add one more slides. So we'll write the program for half adder. Okay, so if you see the half adder circuit, so how to write the program for half adder circuit? Half adder, half adder. Yeah. So first I'll write the program for half adder circuit. Okay. So if you write the program for half adder circuit, half adder. Okay. So if you write the program for half adder, so how to write? So I'm using this one module. Okay. Module. Okay. Module. Okay. My module name. What is the module name? Half underscore adder. Half underscore adder. And here I am initializing the input. Okay, so what are the inputs? Input 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 my input is, let us take one second, somebody join. Yeah, I'm writing for the half adder. I need to initialize the inputs. Okay, so input here itself I'm initializing the input. Okay, so input is what? Input a underscore ha. Okay, ha comma input input b underscore ha half adder. Okay, and next I'm using output. Okay, output so here I'm using behavioral modeling. I need to initialize reg. Okay, output reg sum. Let us take the output reg sum, and output reg let us take carry out. Okay, c out underscore ha. C out underscore ha. Okay, So I initialize the input and output. Next, so here I am using always at the rate star. Star means what? Implication operator. That will be if there any change in the input, there is a change in the output. Okay, always in so always at the rate star. Begin. Okay, begin. I am writing sum underscore ha. Sum underscore ha equal to what? Sum underscore ha equal to, I can write. So what is half adder? Like you have two inputs and two outputs. You already came across half adder, no? So these are the two inputs. Let us take input A and B, and output is sum and carry. Okay, sum equal to what? So here A XOR B, and carry equal to what? Carry equal to AB. Okay, that you know. Okay, so here so I'm writing the data flow modeling. So that is half underscore ha, and by using this cap, that is XOR operation, b underscore ha, okay, and carry out underscore ha. This is equal to what? This is equal to a underscore ha, and I'm using bit level operator b underscore ha, okay, and end module, end module. Okay, so this is my design. Okay, I wrote the design for what? Half adder circuit. Okay, so next I want to write the test bench for this half adder circuit. Okay, how to write the test bench for this half adder circuit? So here you see the test bench for half adder circuit. Hope you understood this program, how to wrote the design for this half adder circuit. Okay, and coming to the test bench. Okay, so coming to the test bench, how to write this test bench means, here you see test bench for this combination circuit. I am writing test bench. If you see, okay, so first you need to like initialize the test bench. Okay, module module. So I'm giving the module name half underscore adder underscore tb. Okay, tb, and here I'm not giving any inputs. I'm not declaring any inputs and output. Why? Because in the test bench I need to give the stimulus. Okay, so that means step one. So this is initializing the module half underscore adder underscore tb, and step one is nothing but you need to declare your internal variables. Okay, so that means there are port rule connections I told you. So that means in test bench the input will be declared in terms of reg data type, and output should be declared in terms of y data type. Okay, so I am declaring reg a underscore tb comma b underscore tb. Okay, a underscore tb and b underscore tb, and output I am initializing as wire sum underscore tb comma carry out. Okay, carry out underscore tb. Okay, these are test bench inputs. Okay, so what is step one? Step one is you need to initialize the declare the internal variables. You need to declare the internal variables. Okay, these are the internal variables I need to declare. Okay, after that what is step two? Step two is instantiate the design in the test bench. Okay, instantiate the design in test bench. Okay, in tb test bench. Okay, how to instantiate? There are two methods are there. One is instantiation by position. Okay, instantiation by position with order list means how you declared your inputs and output, that same order you need to follow. Okay, that is instantiation by position with order list. And next one is instantiation by name. Okay, by name you need to initialize. Okay, so here in the test bench, I am following instantiation by name. Okay, so instantiation by name if you follow, so that means what is my design name? Half underscore adder, and my instance name. What is my instance name? Ha. Okay, instance name is ha. And here how you will get means, here it will be like this. That means my design inputs are there, no, that will come outside the bracket. A underscore ha dot, you will get dot bracket, this is a underscore tb. Okay, comma dot B underscore HA B underscore TB. Okay, so whatever the variables outside the bracket are nothing but design inputs and outputs, and whatever the brackets you indicated inside the bracket are nothing but test bench inputs. Okay, and next dot, so it should be related with dot sum underscore HA, this is sum underscore TB. Okay, in the bracket you need to initialize. Okay, dot carry out C out underscore HA, this is C out underscore TB. Okay, like this is nothing but your initialization, that is connection by name. Okay, in the industry they will follow the connection by name only. So like this you need to instantiate. Okay, so that means if you are horizontally, if you are instantiating means, suppose if you have some 100 inputs are there, one input you are missing, this is that is difficult to trace. Okay, so here if you are like vertically you are instantiating, so it is easy to trace. Okay, that is nothing but half underscore, this is instantiation connection by name. And next step 3 is nothing but initialize the reg variables. Okay, step 3 is initialize reg variables. Initialize the reg variables. Okay, what are reg variables? So I am using initial begin okay, I am using concatenation operator. What are the reg variables? Here you see. So what are the reg variables? I initialize the inputs are reg variables, no, that inputs you need to initialize. Okay, so that means a underscore TB comma b underscore TB, that I am initializing to 0. Okay, you need to initialize the reg variables and end Okay, and next coming to the step 4, driving the inputs for the design. Okay, step 4 is nothing but step 4. Okay, step 4 is driving the input for the design. Driving the inputs input for the design. Okay, inputs for the design. Okay, how to drive the input for the design? First I am using initial. Okay, okay, initial begin. Okay, a underscore TB, that is equal to what I am giving, one tick binary 0. Okay, and B underscore TB equal to one tick binary 0. Okay, and next and after here I am giving 10 time units. Okay, this is my delay. Okay, after 10 time units I am giving a underscore TB equal to what, 0 1. 0 1 means what, one tick binary 0, a underscore TB, that is equal to one tick binary 1. Okay, so I am giving like this. Okay, so for each and every instruction you need to keep semicolon, that is end of the statement. Okay, and after that after 10 time units I am giving a underscore TB, that is equal to 10. So that is this is 1. Okay, after that a underscore, so here after that I am giving this is not there. After time delay I am giving the stimulus. So that means so normally truth table is what, 0 0 0 1 1 0 1 1. These inputs you need to give in the test bench. Okay, so b underscore TB, so b underscore TB equal to what, 1 0, next 0. Okay, after 10 time units after 10 time units you need to give a underscore TB that is equal to 1, and b underscore TB equal to what, 1. Okay, equal to 1. Okay, and next initial begin end and end module. Okay, so like this you need to write the test bench for any combinational circuit. Okay, any combinational circuit. Okay, so like this you need to write the, so this is a basic steps, so 4 steps you need to follow. So what are those steps? First you need to write the design. Okay, first you need to write the design. Okay, what is my design? That means I wrote for a simple half adder. Okay, simple half adder I wrote, and I'm using behavioral modeling. Okay, I'm using behavioral modeling. And next what I'm using next behavioral modeling, next in the test bench. So half underscore adder, so this is my module name, and so within this no need to represent the values. So step 1, you need to declare the internal variables. What are the internal variables? So reg under, so inputs are reg and outputs are wire, and you need to instantiate connection by name. So whatever the variables outside are nothing but design inputs, and output whatever the variables inside are nothing but test bench inputs. And next you need to initialize the reg variables. Okay, so whatever the inputs are there, that you need to initialize. Okay, I am using concatenation operator. Okay, that I am initialized to 0, and I am giving the stimulus. Okay, I am giving the test vectors. Okay, so like this you need to write the program. Okay, suppose if you see the what we call in the Xilinx Vivado. Okay, I think some download is taking place. Okay, one second. Yeah, I open this. I open one file. I will show you how I wrote, and how you can do this. Okay, so here Verilog codes. Mm, yeah, Verilog codes. Let us take level 0. Level 0 even Verilog codes. Level 0. Even half adder. This is the half adder data flow modeling. Okay, data flow modeling. So here I wrote the half adder what for what. So this is data flow modeling, simple data flow modeling. Okay, so here I wrote for half adder circuit. Okay, so if you see this one, half underscore dut input a comma input a comma b output sum comma ca, and assign sum equal to a xr b, assign ca equal to a and b, and end module. Okay, and coming to the test bench, see here, coming to the test bench, yeah, half underscore test bench, here you see here. So that means here if you see, mm, 16. Okay, so this is my half module half underscore tb. So whatever the inputs are there, I need to initialize with the reg data type. Whatever the outputs are there, I need to initialize with the byte data type. And here what I did, so I initialize with the half underscore dut tb, so ab. So this is connection by position with order list. Okay, and initial begin dollar display. This is so a equal to percentage b, b equal to percentage b, and sum equal to percentage b, and carry equal to percentage b, a comma b comma c. Okay, I need to display, and I need to give the text vectors for every 10 time units. I need to see the monitor. Dollar monitor is nothing but any change in the input, you will get the change in the output. Okay, so I am giving the text vectors, that is 0 0 0 1, and after that 1 0. I am seeing dollar strobe also. Okay, dollar strobe, and 1 1 also I am seeing this. Okay, after this I need to use dollar finish. Okay, this I wrote in GVim. Okay, these programs I can execute in the EDA playground also. Okay, suppose if I want to execute in Costa Sim. Okay, or otherwise if I execute in this one. Okay, just file. So create one new project. Okay, create one new project. You need to create one new project. Okay, next, and here I am using so Xilinx Vivado, like I am using half adder. Okay, so half adder I am using. So this is my half adder. So half underscore adder. Okay, this is my project name. Next, next, create my file name. Okay, what is my file name in the GVim? What is there? This is half underscore dut design under test. So copy this, and just paste here. Okay, okay, file is created. Next, next, we give next, finish. Yeah, so it is created. Yeah, my module name is also same. Okay, yes sir, I am keeping yes sir. And next so next so my design is created, see here, and my design is created. Okay, just double click this. Okay, just you remove this, I don't want. Okay, whatever I wrote in GVim, so just copy this and paste in my design. Okay, run this code, means save this code. And in the simulation part also, so you need to write the test bench in the simulation. Okay, so in the simulation part, so add this next, create that file. What is my simulation file? Half underscore tb, no, just copy this. Okay, and paste this, and okay, finish. So in the simulation part, my simulation module name is also same. Yes, the simulation part. Yeah, so my simulation is created. Okay, half underscore tb. Okay, this is my simulation file. Just this you don't want, just you delete this. Whatever the program I explained, no. So this you copy here. Okay, so just you copy here. Okay, so copy this and paste in this. Save this. Yeah, see here, half underscore dut is my design name, and half underscore tb is my what test bench. Okay, here in my test bench I am instantiating my design. Okay, how I am instantiating half underscore dut, no. So that means now in the test bench, that dut file is gone, and this I instantiated, no. I have only two files, that is design source file and test bench source file. Okay, so now what I need to do, so that means run file, run behavioral simulation, run behavioral simulation. I want to see the simulation part. Okay, I can see the circuit also. So here the simulator, whatever the compiler is there, compiler is converting our code into hardware. Okay, just will wait for some time. It is taking time. So I'll cancel this. Yeah, you can elaborate the design. See here, netlist is generating. Okay, netlist is generating. Just we can elaborate the design. How the design will look like. Half underscore dut. Yeah, my device is loaded. See here, half adder is nothing but with XOR gate followed by AND gate. Okay, this is sum and this is carry out. Okay, carry out, and A and B are nothing but inputs. Okay, A and B are nothing but inputs. Okay, I can simulate this also. Okay, I can simulate this. Yeah, yeah, simulation has started. See here. So in the TCL console also you can see the outputs. See here. That means when a equal to x, b equal to x, you are getting sum equal to x. Okay, and a equal to 0, b equal to 1, sum equal to what? Sum equal to 1, carry equal to 0. A equal to 1, so that is 1 0, sum 1, carry 0. And next 1 0, 1 0, sum 1, carry 0. And 1 1. Okay, I given some random cases. Okay, and 1 1 means sum 1 carry 1 1 means sum 0 carry 1. Okay, so in the test bench also you can what text vector we given 0 0 0 1 1 0 1 1 I gave. Okay, after 5 time units you can see in the waveform also fit to page. Okay, and see here. So that means when input is 0 0, sum 0 carry 0. Okay, and next 0 1, when input is like 0 1, 0 1 means what? Sum 1 carry 0. And 1 0, sum 1 carry 0. And next we see in 0 1. Okay, next we seen about the 0 1. I got this waveform like this. You can see the this I can we can see the uh, simulation part also. Okay, yes. Like that you can write the so here actually this is a transcript. So this is my transcript, in the transcript window how I am getting this. Suppose we can run in the Sim also. Okay, suppose if you want to run in the Sim, so this folder is there, no? This off underscore data flow is there, no? So just 1 second, I'm opening this. So just copy this. Okay, copy this, and next what you need to do, you need to open the Sim. I'm opening the Sim. So I'm closing this. This is half adder. Just I'm closing this. Yeah, I open the Sim, no? So I need to run this code in the transcript window only. Okay, cd flower bracket, copy that folder. Okay, so I'm going into that file. ls means it will show all the files. Okay, whatever the files are there it will show. Okay, and next what you need to do, vlog dot dot slash so here which one I need to do, that means here half adder, no? Half adder data flow slash in that what files are there, half adder dut file. This is my design file. Okay, plus acc. Okay, I need to enter. Okay, first before that I need to create the work function. Okay, vlib work and vmap work. Okay, and next next vlog dot slash what is my file name? This is my file name, half adder data flow underscore in this here in this if you see slash half adder data flow, in this what files are there? This is file. Okay, this is my v file plus acc. Okay, you can enter. Okay, I am getting 0 errors and 0 warnings. Okay, again vlog dot slash what is my file? Half adder, no? 1 second. mm, uh, okay, okay, yeah, yeah, see here. So vlog and slash. Okay, slash what is my file name? Half underscore adder data flow slash and so I need to run the tb file dot v. Okay, dot v. Okay, I need to run this file. Okay, vlog dot hash half adder underscore data flow half tb, this one. Okay, 0 or 0 1, and I got half tb, no? Just you copy this. Okay, control c, and I need to go for vsim vsim. So paste this. Okay, enter this. Simulation will start. Okay, my simulation is started. Okay, so my simulation is started, and in this what I can do, so here you have like this TB files are there. Okay, so in this mm, this TB is there, no, this TB is there, no, right click. Okay, this TB, if you click on TB, whatever the design inputs are there, that will be displayed. Right click, add waves. Okay, add waves, it will be added that way, that inputs will be added into this. Okay, add waves means input will be added into this. Okay, and next I need to create run hyphen all. Okay, run hyphen all. Are you sure want to finish means no. Okay, so my I got a waveform. Okay, this waveform I got fit to page, or if you want you can expand also. Yeah, see here, so I can see you can expand also. So here you see, here in the transcript window you got this. Okay, same outputs you'll get: a equal to x, b equal to x, sum equal to x, and ca equal to x, a equal to 0, b equal to 0, sum equal to 1. So 0 1 means someone carry 0, 1 0 means someone carry 0, 1 0 means someone carry 0, like that you got the outputs. Okay, that you can see in the simulation part also. See here, that means here if you expand, that means these are the inputs. Okay, so a0 b0 sum 0 carry 0, a0 b1 sum 1 carry 0, a1 a1 b0 sum 1 carry 0, a1 b1 sum 0 carry 1. Okay, like this you can see. Okay, suppose if you want to like if you want to so don't want to enter all these commands, I want only one command means what I can do means, where I created vlib, no, here this vlib is there, no, this is nothing but transcript, that whatever I showed, vlib, vlog, and run all. So run all is there, no, till here. Just you copy this. Okay, and you create one vim file. Okay, so paste in this. Okay, paste in this, and create that file as, okay, save that file. So where is my path? One second, where is my path? So verilog codes level 0 half header, no, yeah. So here file save. Okay, file save, and you need to go to the path. Okay, so yeah, this kt semicolon verilog codes verilog codes level 0, and which program I am doing, uh, so half adder, no, half adder data scroll. Okay, here so that means I'll give a file name, that means half, or I can use run file also, run dot do. Okay, in this I will give a file called run dot do. Okay, so I'm saving that file. Okay, overwriting. Okay, already file is there. Okay, I'll save this. But, I think in run.do file is there, I think so. Run file is there. Okay, already run file is there. Okay, so here this is my run file. Okay, actually this is my run file. Okay, so here in the transcript window, what I can do, already I am there in this folder. Okay, so I will go for quit sim. Okay, quit hyphen sim. Okay, just I'll click the command. What is that command? Run space do space run dot do space run dot do. It will execute. No need to add that commands. Okay, so directly it is executed. Okay, and next here no, I need to add the waves, where I need to, so see here add waves. Okay, one second, add waves. Okay, add waves, that waves are added to this one. Okay, right click, add waves. Okay, here it is added. Okay, so directly like I got the output, I didn't done anything, just a fit to page. Okay, so it is directly it is running, and then I can see the simulation. Okay, this is main advantages of Questasim. Okay, so directly if you press this command, this will be executed. Okay, do space run dot do means it will be executed. Okay, like this we can see the Costa sim. Okay, so this is about about the programming part.